definition. A subspace, put a little squiggly under there, of Rn is any set S of vectors in Rn such that the following two conditions hold. Condition 1, S is closed under addition. Well, okay, what does that mean? That means that if U and V are in S, then so is U plus V. Our second condition is that S is closed under scalar multiplication. Put a squiggly under there. Again, what does that mean? Well, it means that if U is in our set and C is any scalar, is any real number, then C times our vector U is also in our set. I'm going to box this definition. This is the main object of study in our course. Now, some of you, if you've already been looking at the book, might notice that this is not exactly the same definition as the book uses. The book also includes what I'll call condition 0, that the 0 vector, the vector 0, is in S. But that's not actually anything different than the definition that we already have. Why is that? This condition is already part of 2. Well, why is that? Well, the real number 0 is in particular a real number. So by condition 2, 0 times U is in S if U is any vector in S. So this is for any vector in S. In particular, that means that because this guy is equal to the 0 vector, we conclude that 0 must be in S. So although I don't include that as one of the axioms, in practice, whenever you are checking to see whether something is a subspace, the first thing you want to do is check to see, is the 0 vector in that subspace? Some examples. Rn is a subspace of itself. Why is that? Well, if I take two vectors in Rn and I add them together, they stay in Rn. I'm not going to get more components by adding them together. And similarly, if I take a number like 5 or pi or -16 and I multiply that number by a vector in Rn, I stay in Rn. All I'm doing is making the vector longer or shorter, or making it 0, or making it point the other direction. The set consisting of the single vector 0 is also a subspace of Rn. Let's think why that is. Looking at the first condition over here, the first condition, we need to say, okay, if I take two vectors in the set 0 and I add them together, I'm still in that set. Well, let's see. If I take 0, that's one vector in our set, and the only other vector in that set is, well, it's the same vector. It's the only vector in that set. If I take 0 and I add it to itself, well, that's still 0, which is still in here. And similarly, if I take any number, if I take, say, the number which I'm going to call c, which is any real number, and I multiply it by the vector 0, that's still going to be 0, which is in here. So therefore, I can conclude that the set consisting of just the single vector 0 is a subspace of Rn. As I've said many times in this course, the prototypical examples of subspaces are lines and planes through the origin. In the next video, I'll talk about how you can generalize the method that I'll use to show that these in fact are subspaces to show that any span is a subspace. The remainder of this lesson will be concerned with how to get a subspace from a matrix. We'll talk about 3 ways to do that: the null space of the matrix, the row space of the matrix, and the column space of the matrix.